We have all heard about the recent agreement to combat climate change agreed to by 195 countries. In spite of the seemingly overwhelming support for the Paris Agreement, a small but loud group has formed to protest the agreement. They call themselves the Anti-Paris Agreement Group. I went to the home of Don Posey and sat down with him and Francis Neptune, two of the founding members of the group, to find out what their group is all about. Well, thanks for agreeing to meet me, guys.
Thanks for having us.
So, Francis, whenever people hear that you're against the Paris Agreement, they automatically assume that you are a denier of climate change.
We believe fully in climate change and global warming. The evidence is incontrovertible. We just think that the Paris Agreement and the actions taken are going in the complete wrong direction.
Right. The agreement is entirely based off the assumption that carbon dioxide is the gas that contributes the most to climate change. That is simply not true. In fact, what turns out to be the gas that contributes the most, up to 70%, is water vapor.
Water vapor?
Water vapor. The Paris Agreement does not even mention the contributions of water vapor. How can we expect to combat climate change without addressing the biggest part of the problem?
This is where our proposal comes in. Although it has been rejected by every climate change scientist and activist in the world so far, we think that in order to best reduce the effect of water vapor, we should burn as much fossil fuels as possible and release as much gas into the atmosphere.
So let me get this right. You want to burn as much stuff as possible to release as many greenhouse gases as you can because you think it'll decrease the water vapor in the air and thus change our global warming problem?
I could not have said it better myself.
So I'm very excited to see how this all works.
Well, it can be explained very simply by something we experts like to call phase diagrams.
What is a phase diagram?
I'm glad you asked. As a matter of fact, I happen to have one on me right this very moment. This is a phase diagram. It shows the state of matter for a certain compound or element, in this case, water. As you can see here, this is solid water, ice. Liquid water, as found in the oceans, and water vapor, the dangerous stuff found in the atmosphere. It's simply a measure of the state of matter at varying pressure and temperature. As the pressure increases, the temperature at which a liquid turns into a gas also increases. This temperature is known as the boiling point, although it is really more of a boiling line. Similarly, the point or line where a liquid turns into a solid is known as the freezing point. Fun fact, just about every compound has a positive slope on the solid to liquid border, but water does not. This points to the fact that ice has a lower density than water, which makes it float in water, insulating the rest of the water from the outside air and allowing life on this wonderful planet.
If you notice, there's a point on the phase diagram where the solid, gas, and liquid areas all intersect. This is known as the triple point. It's where every single phase transition is occurring at the same time at the same rate.
So it's basically like a 3-point line for compounds?
No.
You see, at every border between sections of the phase diagram, the compound is in equilibrium. If it is on the border between liquids and gases, the liquid is turning into a gas at the same rate that the gas is turning into a liquid. Therefore, there is no net change. Let's use an analogy here. Polar bears are always dying and being born. If the death rate and birth rate are equal, there will always be an equal number of polar bears in the world, although they will not be the same polar bears. If we let global warming go unchecked due to the terrors of water vapor, the polar bear death rate will increase. Polar bears will still be born, but polar bears will die at a quicker rate, and eventually there will be no polar bears left.
So what you're saying is that the polar bears are evaporating?
No.
So why is water a liquid at room temperature, whereas carbon dioxide is a gas?
It all comes down to intermolecular forces. The stronger the intermolecular forces in a compound, the more likely that it is a solid or liquid at room temperature. The weaker the intermolecular forces, the more likely that it is a gas. The intermolecular forces are often grouped together as the van der Waals forces. The weakest van der Waals force is the London dispersion force. London dispersion forces occur when the electrons in a molecule instantaneously line up to make the molecule polar. Although this only happens for a split second at a time, it is enough to give the molecule an attractive force with other molecules whose electrons line up. Dipole-dipole forces are the next weakest. They occur when either due to the shape of the molecule or its bonding, one side of the molecule is slightly positive and the other is slightly negative. This allows them to attract to other similarly polar molecules. Hydrogen bonding, the strongest van der Waals force, is a special case of dipole-dipole force. It occurs when hydrogen is bonded to a highly electronegative element, specifically oxygen, nitrogen, or fluorine. So let's look at carbon dioxide. Carbon dioxide has a carbon in the middle and oxygens on either side. The bonds are polar because carbon and oxygen have different electronegativities, but because oxygen is on both sides of the carbon, the pool that goes to the left is the same as the pool that goes to the right, so it cancels out and leaves the molecule non-polar, which means that it is acted on mainly by London dispersion forces, and thus it's a gas at room temperature. Water, on the other hand, has an oxygen with two hydrogens coming off at an angle this way. So the bonds are very polar because oxygen and hydrogen have very different electronegativities, and they're both pooling this way. So that leaves water as a very polar molecule, and thus it is liquid at room temperature.
Okay, I think we've gotten a little bit off topic. While you guys have been explaining liquids in a very relevant, entertaining, and thorough way, we need to talk about global warming.
Right. Well, you see.
Alright, I gotta cut you off. Commercial break. We will be right back with 60 Minutes in 60 seconds.
This beautiful creature is the basilisk. Not the Harry Potter basilisk, but it does have some killer moves. However, the basilisk's dance floor is the water. Crikey! Aptly named the Jesus Christ lizard, the basilisk can skim across the water due to an interesting property of liquids, but water in particular. It is known as surface tension. Liquids are held together by intermolecular forces such as hydrogen bonding in water. Depending on how strong the forces are, an object that moves through the liquid will experience drag due to the viscosity of the liquid or its resistance to flow. At the surface, the attractive force is concentrated out and down, leading, in essence, to a membrane on top of the liquid. The lizard is able to spread its weight enough over a large area, allowing it not to exceed the force that holds the water together, allowing it to run on water and be safe from the crocs that lurk beneath in the land down under. We cannot allow such a wonderful creature to go extinct. Although it is not yet endangered, who knows, it may become so at some point in the future, the very, very distant future. Donate now to the Basilisk Defense Fund, also known as the BDF, so that we are prepared to defend these magnificent creatures. Call 1-800-BASILISK today. To save these wonderful basilisks, stop burning fossil fuels.
We are back. So guys, in theory, what you were saying is we need to burn more fossil fuels.
Our goal is to keep the biggest contributor of global warming, water, H2O, in its liquid state, an incompressible state where the molecules are set in a certain volume but no set shape, and where the molecules are in constant motion rolling over the other molecules. We saw through the phase diagram that there are two ways to turn a gas into a liquid: decreased temperature or increased pressure. If we could decrease temperature easily, we would have no problem stopping global warming. However, my friend working on the larger-than-Earth refrigerator failed. So, we must therefore increase pressure. To do this, we need to vent as many gases into the atmosphere as possible. We need to burn as much fossil fuels as possible and free all the trapped gases on the planet if we want to have a chance to stop global warming.
Your methods of doing this are quite radical. You have started forest fires, burned coal seams, vented out the gas in Goodyear's fleet of blimps, emptied the air out of half the scuba tanks on the Great Barrier Reef, and even party crashed a 4-year-old's birthday party and popped all the helium balloons. This is not even close to a complete list.
I would like to point out that none of those events have ever been conclusively linked to us. We're a political organization. Our official activities are lobbying and fundraising. However, we are very supportive of the goals that all of those things have achieved for the planet.
Come, I'll show you around my house, show you some of the things I do to do my part for the planet. This is one of the most inefficient furnaces available, and I always have it running along with my air conditioning. I always have all my appliances on at all times. My cars are the biggest gas guzzlers the economy can provide. I always leave the gas on my stove on at all times.
So that's what that smell was.
Partly. The other part is the engine that I always have running in my closet over here.
Wait, why is there a campfire in your closet?
That's not actually a campfire. It's leaded gasoline that we're burning in there, so you're probably just hallucinating right now.
So you know leaded gasoline is a very dangerous liquid and has been banned in the U.S. for years because of its health hazards.
Yeah, but we get it from Zimbabwe.
I need some fresh air.
I'm sorry, Doctor, but 60 Minutes cannot support your theory. You seem to be taking this pretty well for the loss of your house.
Oh, I may have lied a bit about this being my house. Oh, no, my house! My house!